Hello, and welcome to BME 295, Intro to Electronics, tutorial on LTSpice of resistive circuits. So, as we probably discussed in class so far, one of the most powerful tools we have in understanding and analyzing circuits are programs called SPICE simulators. And today we're just going to go through a quick tutorial on how to set up a SPICE simulation using purely resistive circuits. So hopefully you've installed this on your computer. If you have not done that yet, please go to the LTSpice website, download that and install it, and then continue this video once you have it installed. I highly recommend going through this with me, pausing where you need to in order to find different commands and the like. So let's go ahead and begin. Now, there are a couple important version differences between Windows and Mac. When you run LTSpice, hopefully you see a screen similar to this. It will look a little bit different on Mac. If you have a Mac and you also have a Windows boot on that Mac, I highly recommend installing in Windows. But it will also work on pure Mac builds, just with a couple of trickier spots that I'll cover here. So if you're in Windows, you'll see a nice toolbar up here that will give you some shortcuts. This is missing in the Mac version, but we can get to all of these by simply three-finger clicking or right-clicking in the Windows case. So let's start a new schematic. So if we right-click or three-finger click and we click New Schematic, we'll see this screen pop up. So this is your workspace. If you're in Windows, you luckily have a resistor component up here, just right on your toolbar. In Mac, this will be a little bit more difficult. You can right-click or three-finger click, go to Draft, and then Component, and you'll be able to find all of your components here, resistors included. So let's find the resistor. In this case, we have two resistor, or res and res2. Res is fine here. There's no difference, just the symbol is different. So let's place a resistor by clicking OK. You'll notice that it automatically generates a resistor with a name, in this case R1. The name helps you keep track of your resistors, and this will become important during more complicated builds. So let's place a resistor here. If I wanted to rotate that, I can hit Control R and get a rotated resistor. So let's place that here. Now it will automatically auto-populate for a second resistor. If we right-click or three-finger click, we will get rid of that. Now we've had a little bit of a discussion on voltage and current, which are our two main parameters of interest in circuit design. But just as a quick overview, every circuit requires either movement of electrons through it or a potential difference in energy in order to drive it or run the circuit. These are inexorably linked by Ohm's law, in that the voltage is equal to the current times the resistance. I highly recommend getting a handle on voltages and currents before moving forward. If you have any questions, you can refer to the slides or directly contact me. I'd be more than happy to help out wherever I can. So with circuits like this, remember, one of the ways that we can drive them is with a voltage source or a potential difference. To get to a potential difference, Windows users, you can hit the Components button. Mac users, you can three-finger click. Windows can also right-click, go to Draft, and Component here too. There are some hotkeys. I'm currently on a Windows boot, so I'm not sure if these are different between Mac and Windows, but you can see those, and that might be an easier way to do things. So, Component here. This will bring up this screen. Now, we have our sources, a current source, which will drive a current, and a voltage source. For most circuits that we'll be dealing with and that you'll be dealing with throughout your engineering career, voltage sources are the most common, and that's what we'll be doing in the pre-lab as well. So let's place a voltage source. So we've got our voltage source here. Again, I'll right click to get rid of that extra voltage source here. And we've got our very first simple circuit. Now we need to wire up this circuit. You can get to that, oops. Sometimes the screen will move on you in weird ways. You can get to that, Windows users, again, with wire, Mac, or if you want to do this on Windows as well, you can right click and get to draw wire. So we'll connect up this circuit. Now a reminder, current has to flow through a complete circuit. So we'll need to make all of our connections secure here and set this up. So we have a circuit, probably something similar that we've seen in class so far. But something that's different that will become apparent why we do this in just a couple weeks when we talk about nodal analysis methods. Remember that a voltage source, when we talk about voltages, we talk about voltages across elements and currents through elements. Voltages across because remember, this is a potential difference, meaning that it has to be relative to some other value. So in circuit design, we create something called a ground, and the ground is a reference, usually of 0 volts. So we always need to reference our voltage sources to something, and 0 volts is easy. If we look across here, because there's a resistor here, and because voltage equals current times resistance, well, we're going to have a potential difference between these 2 points because of the resistor. And so that probably won't make a good reference because there's inherently a potential drop. But we notice here between this point and the negative terminal of the voltage source, it's just this connecting wire. And wires, by definition, have a 0 volt reference. So we can set a reference, which is demarcated by the ground or the triangle symbol here. So we'll click. And again, Mac users, you can get to that here with, I always have to find this one for me. Give me 1 second. Yes, so this one you'll have to go to label net, and then you can click ground and clicking OK. That will create a ground symbol as well. Okay, so let's wire up our ground. Now, what have we done here? A couple of important things. We have set up a voltage source and we've said, here is our measuring relative point. So the voltage will always be measured relative to this point, which by definition we define as 0 volts. Notice what happens here when there are multiple connections in SPICE. There forms a block. Like, so if there's more than a connection point, say here we have 2 connection points, if these are indeed connected within SPICE, you'll see a bluish block. If you're trying to connect 2 different terminals and you don't see this, that means that they are not connected or that you just have a singular connection, as is the case of this resistor. So something to keep in mind when you're troubleshooting your circuits. So next thing we need to do is give these some values. So let's call this 9 volts. So if we have 9 volts here, and I'll explain how I got to that here. With our resistor, if we right click it, or 3-finger click in the Mac case, we can specify a resistance value. Now, it might be tempting just to put something like 2, that would make things easy, but just something to keep in mind due to power constraints when we're dealing with circuits, we're oftentimes dealing in the kilo ohms or the high hundreds of ohms. So that's the convention I'm going to follow here. So here, if I wanted to say 1000 ohms, which is a kilo ohm, I could specify 1000, or a neat little shortcut here is putting K gives us 1000 ohms as well. If I wanted 1 million ohms, or 1 times 10 to the 6, I can type capital MEG, and that will give us 1 mega ohm. If I wanted a milliohm, which you don't do very often, but occasionally it comes up, you can do a lowercase m, and that will give you a milliohm. So let's stick with the kilo ohm here. So we have 9 volts, and again, you right click here, The series resistance, we'll introduce that here in a later video, but for now, don't worry about it. We have 9 volts here and 1 kilo ohm here. So if we did the math, I'll let you take a second. What current should we expect here by Ohm's law? If voltage is equal to the current times the resistance, then our current should be our voltage divided by the resistance. So take a moment and calculate that. Okay, so now let's move on. And one thing we need to do in order to see the voltages and currents is to simulate the circuit. LTSpice has a lot of different simulation methods. For now, we're going to be worried about the DC operations because we're dealing with a direct voltage and a direct current source. So to do that, Windows users, you get it a little bit easier again. If you hit Simulate, edit simulation control, that will bring up the window. Mac users, you got the 3-finger click, and then you can go to edit simulation command here. So Windows users have something nice here in that we've got a GUI. For Mac users, you'll have to put in these commands yourself. So I'll show you how to do that here in a second, but the analysis that we want to run is a DC operating point, which is just a DC analysis. So Windows users, you can go to DC operating point, click OK, and notice that we'll bring out a command .op. So we place that here, and that will do the operating point for us. Again, Mac users, you will have to hit the edit simulation command and type in .op and place it on your schematic by hand. If you have trouble with this, let me know. Sometimes it can be a little finicky, but if you go there, hit .op, it will do the same thing. All right. So now we're ready to run. So if we right-click, hit Run, a screen will pop up, and this is the operating point. Now, a reminder, we have voltages across elements and currents through elements. So we have the current through resistor 1 then is equal to 9 milliamps. Now, something that's a little bit odd about LTSpice is something that you have to keep in mind when you're doing this, is that typically we follow the passive sign convention, which is something that we'll talk about in class. However, for currents, LTSpice does not follow the passive sign convention. We will follow the passive sign convention. So anytime you're looking at currents, and this is important, anytime you're looking at currents through this, you'll have to flip the sign, or else the answer might be marked incorrect on your pre-lab. So always flip the sign. And so we can also look at the voltage across the resistor, which is here, which is just 9 volts. Now notice here, the way that this operates is that we have different nodes. Nodes you can think of as connection points. Because we are looking at voltages across points, what this is saying is that at this node, the voltage between these 2 points, a node is from here to here. And because it's the first connection that we make that is not the power supply, we call this node 001. And we get that, as you expect, 9 volts. Okay, so that's our first simulation done. Congratulations, that's good. There's a lot more complicated things that we'll do, but we'll start introducing some things that we can do here. So let's say we made a mistake or we wanted to add in another element. We can go to the cut command, which is for Windows users right up here with the scissors. For Mac users, you will have to go to edit, delete, which will be the same command here. So we'll cut out that wire and we'll add in another resistor. So we make our connections here. Let's give our resistor a value of also 1K. Now, if we have a series resistance here like this, what do you think is going to be the voltage across this element? Something to ask yourself. We'll see that here in a second. So go ahead and think about that a second. Maybe pause it if you want, do a little math, because this actually, despite its simplicity, is one of the most valuable circuits that we can use. And I'll show you why here in a second. Okay, well, we still have our .op command here, so we're ready to simulate. So we'll just simply hit run, and there we go. So let's look at our voltages here. So notice here we've created a new node, and we're measuring that node from here to ground. So hopefully you guys have convinced yourself that the voltage across this point is half of what the input voltage is. This is what we call a voltage divider. These are extremely useful for, especially for medical electronics, for balancing voltages. That will become apparent later on as we go throughout the semester, but it's kind of cool to think about as well. Now, what do you expect the current to be? Well, the current is going to move through these elements equally. So we're going to have a fixed current of 45 milliamps. Now, notice the weirdness of the sign convention here. These are the same currents moving through, but this will be a positive, sorry, I said 45, 4.5 milliamps as well. So be careful with that. All right, so let's make things a little bit more complicated. What happens if we add in another resistor in parallel? Well, let's go ahead and hook that up. And just to show you some errors that can occur, let me try to simulate this without connecting this slug of the terminal. I hit run. I can't find a definition of model R. Well, that might be because I didn't give it a resistor value. Let's say 5K. Try again. Now, notice what's happening here. The simulation still runs because current's allowed to flow through here. This element has an open circuit, meaning that there's going to be zero current through this point. So to fix that, we simply connect up a wire here. Now notice we've got connection points here and here with the blue boxes that tell us that we're indeed connected. I hit run, and now we start getting things that start making a little bit more sense. Notice what's happening here. We have a current entering this node here, and this current is going to be about 0.8 milliamps. Now notice what happens here is that our current is now being divided in an interesting way. This is known as a current divider, and we'll see how that can come into play later in class. And with that, these are some little functions, a brief introduction into LTSpice with resistive circuits. We can make this arbitrarily complex, but these are the tools that you'll need to do the first part of this course, as well as the pre-labs themselves. So go ahead and try the pre-lab associated with this lecture. As always, if you have any questions, feel free to email me, and I'd be happy to help wherever I can. Thank you very much.